Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am assistant professor from Department of Computer Science at Aggregate College, University of Delhi. So within this series of design and analysis of algorithm of lectures, we have our today's topic as aggregate method, which is basically a topic under amortized analysis. So please recall that we have already covered, we can say a couple of topics of this amortized analysis, that is what actually amortized analysis is, how many methods are there, and then within that the first method, which is aggregate method, we have taken two examples. So let us have a quick recap, and then we will start today's lecture, in which we are going to have one more example of amortized analysis using this aggregate method technique. So within this aggregate method, we need to determine the total cost Tn for a sequence of n operations, and we will be calculating the amortized cost per operation as average cost, which is going to be T of n divided by n. So here this is what we perform in aggregate method. As contrary to aggregate method, we have other two methods, which are accounting method and potential method also. So accounting method is about assigning cost to each operation while overcharging some and undercharging others, where the basic idea says we early overcharge the operations, and through this technique we prepay for the later undercharged operations. This is what accounting method says, while potential method says rather than having the whole kind of cost or credit with the operation, a potential energy, which is a kind of, we can say, a credit with the kind of new term, we can say a potential energy is associated to the data structure, instead credit to the operation. So this is what we have taken a recap of the three methods, and in order to show the working of aggregate method, we have seen two examples. One was dynamic table, how this dynamic table data structure is using amortized analysis to have kind of tighter and good bounds for their operations, and another one which we have seen was an augmented stack, which is a stack with the additional operation called multi-pop, and that additional operation multi-pop is capable of popping several objects at once. So these two examples we have already covered. Now we are coming to our example of a binary counter. So that binary counter is going to count up starting from 0, and this counting will be taken place by means of a single operation, which is the operation of increment. Now what do we mean by incrementing a binary counter? So by incrementing a binary counter is basically a problem of implementation of a k-bit binary counter whose length, whose number of bits is k, and this is going to count upward from 0. So initially the value of the binary counter is 0, then it will become 1, and then it will become 2 and 3 and so on and so forth, but in terms of binary numbers, because it is a binary counter. So to implement this binary counter, we have taken a data structure which is an array. So that array is having that array is A, let's name that array as A, and that is having we can say what size starting from 0 to k, indexing is starting from 0 to k minus 1. So total size is k, which is the number of bits, and length of A is equals to k. So let's say a binary number which is x, that is stored in the counter, has its lowest order bit in A0 and highest order bit in the index or at the index of ak minus 1. So initially, let's say we have the number 0, or we can say the number which is x is 0, and thus my ai is 0 for all the i's, that is for I ranging from 0 to k minus 1, each and every bit is 0. So my whole ai is 0 when we are talking about x equals to 0. Then what are we going to do with this binary counter? So first of all, let us try to understand what this binary counter is with the help of a figure. So as you can see on the figure, we have a 8-bit binary counter here. So the numbers, or sorry, the indexing of the array A is ranging from A0, A1, A2 till A7, which is k minus 1. At the top of the figure, if you can see, we have the counter value as 0 and all the bits there are 0. When we increment, the value of counter will become 1, and the binary equivalent of 1 in the format of 8 bits will be stored in the array. So which is essentially 0 1 at the kind of, we can say, at the bits of A1 and A0. Then we have incrementing the counter value, again we have 2. Now the binary number corresponding to 2 will be stored in this array. Then we have 3, and so on and so forth. So at the rightmost we have one column which says total cost. I'll be coming to that total cost thing in a moment. So this is what basically a binary counter is, and this is what my binary counter looks like. So basically we can say it is simply an array starting from 0 to k minus 1, and whatever the counter value is, binary number corresponding to that counter value will be stored within that array A. So this is what the agenda is. Now what do we want to do? We actually want to add 1, and now we can say, as my binary counter is kind of, we can say, limited to 8 bits, it is not only addition of 1, but it is addition of 1 modulo 2k, 2 to the power k, because we will be resetting after reaching at the end. We will be resetting to the resetting the counter to value 0. So for this kind of increment operation, we have we have a pseudocode which says we need to increment the array A, and initially my I is 0, while my I is less than length of A and AI equals to 1. What do I need to do? I will be saying ai equals to 0 for every I in the loop, and we will be incrementing I every we will be incrementing I by 1. So wherever I am having 0, I will be saying it, wherever I am having ai as 1, I will be doing ai as 0, and this process will be repeated for we can say is for the whole number of bits. And when my I is less than the length of A, then A of I is equals to 1. So this is what the increment operation is. So basically increment operation is incrementing, or every time it is adding 1, basically 1 modulo 2 to the power k to the value of the counter. So earlier it was 0, then it will become 1, then it will become 2, 3, 4, 5, and so on and so forth, and the counter will go till 16. This is what we have shown in figure, but this counter is having kind of, we can say, many other possibilities, because there are total 8 bits. So at the end, when all the 8 bits will become 1 1 1 1 1 1, and then the counter will be reset to 0. So here whatever we have shown in the figure is actually a binary counter which is incremented 16 times, starting with the initial value of 0, and it is ending with the value of 16. This is what have been shown in the figure. So a binary counter incremented by counted number of times, which is 16, it has started from 0, then it becomes 1, then it becomes 2, and so on and so forth till it reaches 16. So this is what we have shown. Now at the start of each iteration of that while loop, which we have seen in the pseudocode, we wish to add 1 to the position I. So if ai is equals to 1, then adding 1 is going to do what? Let's see. Then adding 1 will flip the bit to 0 in the position I. At the position of I, the bit will be flipped to 0, and it is going to yield a carry of 1 to the next position or to the next bit, which is I plus 1. So basically, if my a of I is equals to 1 and I am going to add 1 more into that, this is going to flip the bit to 0 at the position I, and it will yield a carry of 1 to be added to the position I plus 1 on the next iteration of the loop. So this is basically a kind of, we can say, a trivial mechanism when we talk about addition of 1 into any binary number. So this is what it is being done in the while loop of that pseudocode. Or if the conditions are not being satisfied, the loop is going to end, and if I is less than k, and we know that a of I equals to 0, so adding 1 into the position I, flipping 0 to 1, and it is taken care in line number 6. So whatever flipping it is ai is equals to 0 and we are adding 1, so ai will be flipped from 0 to 1, or vice versa. Both the conditions have been taken care in the pseudocode, which I have already shown. So the cost of each increment, if we trivially see, or if we trivially want to analyze the cost of this increment operation, so what is the kind of basic mechanism which is taking place here? So basic mechanism which is taking place here is just kind of, we can say, flipping of various bits. So cost of each increment operation will be linear in number of bits flip. How let's say we have there are we have the counter value as 2, and then we are going to have counter value as 3. So we can say 3 bits have been flipped, and so on and so forth. So the cost of each increment operation is going to be linear in number of bits flipped. That's a kind of we can say trivial thing which we can observe. And in case of analysis, we can say a single execution of an increment operation. Mind it, here we are talking about a single execution. A single execution of increment operation is going to take time k, because that is the number of bits in the array in the worst case, in which, and when this worst case is going to happen, where the array is containing all ones. Let's say at the kind of last position we have all ones at all the 8 bits, and we need to increment this array again, and I have already told you that this increment is actually modulo 2 to the power k. That means this is going to give a reset condition to this binary counter. So all the number of bits which are 1 here will be flipped to 0, and my binary counter will be reset again. So this is the worst case which can happen, and in this in this increment order k time will be taken, because k is the number of we can say bits there. This is we have already seen in the structure of the array. So one increment operation is taking order k time. So simply a sequence of n increment operations on an initially 0 counter is going to take order n multiplied by k in the worst case. So here we are talking about the worst case. So a sequence of n increment operations is going to be kind of order nk of order nk, which is the cost, or which we can say is the time complexity of this n increment operations. But as I have told you that this is a kind of very trivial analysis, or analysis which is at the macro level. Looking at the micro level, or looking minutely, we can easily say that we have observed that not all the bits flip each time when increment is called, and this is what is happening in the array. If you can recall that figure, each time when your increment is happening, you can see it on the screen. Every bit is not being flipped. Let's say, for example, we talk about the counter when it is having 3 as the value, and the next increment causes the value to be 4. So from 0, 1, 1, the bits which are kind of flipped is the bit at the position A2, which is flipping from 0 to 1, and the bit which is at position A0, and that is being flipping from 1 to 0. So this is what the change we are having. So every time, can we say that all the k bits are flipping? No, it is not happening, except one instance which we can say that all are 1, and then at the time of reset of the counter all the bits will become 0. So that is the only operation in which k bits are being flipped, while in other operations we cannot say that all the k bits are being flipped. Yeah, fine. So now let us try to understand what all are the what all are the bits which are being flipped. So in that particular case, we have seen that A0 will be flipping each time increment is called. So A0 is flipping, A of 0 is flipping every time. The next higher order bit, which is which is stored at the position index number 1, which is A1, it is flipping every other time, every alternate time it is flipping. Then coming to the next kind of bit, which is A of 2, we can say it is flipping every once in every 4 times. So a sequence of n increment operations causes A1 to flip n by 2 times. Similarly, the bit which is A2 will flip every 4 times, once in 4 flips, or once in 4 increments, which is basically n by 4 times in a sequence of n increments when we talk about. So please notice here that we are not talking about a single increment. As we ultimately want to perform amortized analysis, we are concerned with sequence of operations. So we are considering that whole sequence of n increment operations. So A0 is flipping every time, A1 is flipping n by 2 times for n increment operations, A2 is flipping every n by 4 times. This you can verify from the figure, which says, if you can see the last bit, which is A0, and now look at the sequence: 0, then for next value it is 1, then for 0 it is 0, then 1, 0, 1, 0. So it is being flipped every time. Now look at the A1 bit carefully. Is it being flipped every time? No. For 0 and 1, the value is 0, A1 I am talking about. Then for 2 it is 1, for 3 it is 1 also, then for 4 it has become 0, then for 4, 5 it is 0, then for 6, 7 it is 1. So basically it is flipping every alternate time. And looking at A2, you will notice that it is flipping after every 4 increment operations. So we can say, in a looking at this pattern of flipping the bits in the binary counter, we can say in general, for I equals to 0 to log n, bit ai is going to flip n by 2 to the power I times in a sequence of n increment operations on an initially 0 counter. So basically I am just repeating it again. For I is equals to 0 to log n, when I ranges from 0 to log n, bit ai is going to flip n divided by 2 to the power I times in the sequence of n increment operations on an initially 0 counter. And for I, which is out of the range of log n, where I is greater than log n, bit I never flips at all. So this is what a general observation, or we can say minute observation we are having. So total number of flips in the sequence is going to be bounded by this series, where we can say total number of flips is going to be summation of all the flips, obviously, and here I is ranging from 0 to floor of log n, and the expression is n divided by 2 to the power I. So I ranges from 0 to log n for n divided by 2 to the power I, which is the general kind of which is the general number of times for every number of times the bits are being flipped. And this whole is, we can say, when we take out the term n, which is a kind of, we can say, constant in terms of, if we are summing up the series from I is equals to 0 to log n. So we have taken out n, and this is the term on the left side is strictly less than the term where I is equals to, I ranges from 0 to infinity, because in the first term I is ranging from 0 to log n, and if we increase the limit from I is equals to 0 to infinity, definitely I is equals to 0 to log n is less than that. We have taken n out, and what are we left with? N into summation of I is equals to 0 to infinity 1 upon 2 to the power I, and this I is equals to 0 to infinity 1 upon 2 to the power I is essentially equals to 2 by summation of its series. So finally we ended up with the term 2n. So we can say I is equals to 0 to log n when summed up when n upon 2 to the power I, when summed up for I is equals to 0 to log n, is going to give us 2 multiplied by n, or simply 2n. So basically we can say the worst case time for a sequence of n increment operation on an initially 0 counter is therefore order of n, because we have encountered a term which is 2n. So looking at the order, we can say the worst case time for a sequence of n increment operations on an initially 0 counter is of order n. So if order n is the worst case time for a sequence of n increment operations, and we need to determine the amortized cost for each of the operation, and we have seen it for n sequence operations. So we can say the amortized cost is going to be order n divided by n operations, which is order 1. So basically amortized cost is order 1 if we talk about a single operation, because when we talked about the sequence of operations and minutely looking at the binary counter, we observed that each bit is not being flipped every time, and with that analysis that bit is being flipped only the log n of its position time. So we can say worst case time for n increment operation is not kinds of n square or any other, but it is trivially an order n, which is a term equals to 2n to be precise. So 2n precisely is order n. So the amortized cost for each of the operations is we can say order n by n averaged out, and this is what is equals to order 1. So, here in this lecture we have seen with a quick recap of all the three methods of amortized analysis, which are aggregate analysis, potential analysis and accounting method. We have taken a quick recap, and then we have seen the example of incrementing a binary counter, where increment is the main operation, and we have seen the trivial kind of analysis when we perform it for sequence of n operation is something different, and when we perform it we can say a tighter analysis. The earlier analysis was correct, but it was not tighter, and then we have seen that number of bits flipped, which is actually a kind of, we can say, an operation which is adding cost to the operation of increment. So, we have seen how many bits are being flipped with each and every increment operation. So, by going into detail of that number of bits being flipped, we have analyzed that the total amortized cost for n increment operations is order n, where the value of the counter initially is 0, and therefore, the amortized cost of each operation is order 1, which is, we can say, a bounded bounded cost. So, hope you have enjoyed the lecture. Thank you for a patient hearing.